Australia's Uranium Opportunities by Keith Alder. Recorded by Logan Smith with the permission of the Alder family. Chapter 6. The Changes in Research Program, 1966 to 1970. It is well known by those responsible for the direction of research programs that one of the most difficult tasks a director faces is to stop a project when it is clear that it has had its day, and usually that it would be better to do something else. I should know. This is hard enough when it is a particular research topic in a specialist field, but it is much worse when the decision is to stop a project which involves many professionals in different disciplines, working in a coordinated manner. The decision by the Commission to terminate the HTGR program and change to a different field was not popular at first with some of the staff. But it was a necessary step, and at the time, quite clearly in the right direction. At that time, 1966, the use of nuclear power was expanding at an ever-increasing rate overseas. The costs were favourable in relation to those of power from fossil fuels, and there was beginning to be a worrying awareness of the finite resources of coal and oil, being used increasingly to burn in boilers. There was at the time little awareness of atmospheric pollution, and very little anti-nuclear activity. It therefore seemed responsible for the AAEC to look at realistic prospects for nuclear power in Australia, and it appeared likely that it would be introduced in the 1970s. In that case, it would almost certainly be by introduction of one of the water-cooled reactor systems, and it was the Commission's view that work should be undertaken to establish expertise in the technology to prepare for that future. Fortunately, many aspects of the various systems are common technologically, so it was not difficult to establish research topics which would be meaningful to any of them. For example, research on zirconium and its alloys, and on uranium dioxide fuels, is common to all water-cooled reactor concepts, whether using natural or enriched uranium and ordinary or heavy water. However, the Commission chose to put some emphasis on the problems of heavy water systems because of the characteristic mentioned earlier. Some of them could run on natural uranium, and Australia could have the possibility of making her own nuclear fuels from indigenous uranium. It was at about this time that it began to look as if we in Australia are richly endowed with uranium resources. Under the Atomic Energy Act, all discoveries of uranium in Australia had to be reported to the Commission, so we were well aware at all times of the growing resources. Until that time, uranium production in Australia had been on a relatively small scale, from mines in South Australia and at Rum Jungle in the Northern Territory. However, discoveries were being made of larger scale deposits, and of course, subsequently, we have learned that we have at least a third of the world's readily extractable uranium. That also we shall look at later. So the new research program was directed toward water reactor systems, with some emphasis on the heavy water moderation and with considerable emphasis development of know-how for the eventual manufacture of nuclear fuels from Australian uranium. We retained one small segment of our gas-cooled reactor research in the Engineering Research Division, which had developed some ideas for a very small power reactor using a pebble bed core and gas cooling to operate a gas turbine, rather than using the hot gas to raise steam. They had constructed an experimental reactor, but without the nuclear fuel, and used a high-powered gas burner to heat it, the hot exit gas driving the turbine. They considered that the concept could be developed for a once-through air cooling if the ceramists produced fuel pebbles with adequate fission product retention. This project continued on a small scale for the next 2 years and produced some interesting new ideas on how to handle the pebble bed. The project was the particular interest of the chief of the division, Mr. G.W.K. Kim Ford, who christened it the Australian Beryllium Oxide Reactor with Integral Gas Turbine, Aborigine Primus. Primus for the first. We also began a small project directed towards development of technology for enriching uranium. At the time, this was highly classified, i.e. secret, everywhere in the world because of the possible uses of such technology to produce weapons-grade enriched uranium. It is still classified. It should be noted, though, that weapons-grade uranium is highly enriched to as much as 93% U-235, whereas power reactor fuels seldom exceed 3%. Research reactors, however, mostly use higher enrichment concentrations. For example, HIFAR initially used fully enriched material, which in practice meant over 90%. In recent years, throughout the world, enrichment level for research reactors has been dropped, usually to less than 50% U-235, to facilitate safeguards against diversion of highly enriched uranium, HEU, to weapons. There were several reasons for beginning our study of enrichment technology. Firstly, knowing that most of the world's future power systems would use enriched material, and that Australia had the potential to be a major nuclear fuel supplier. There were obvious commercial advantages envisaged if we could sell an upgraded product, enriched uranium rather than mined concentrate, yellowcake, or better still, finished fuel elements. And enrichment technology was a closely guarded secret by those who had it, the USA and the UK, as far as we knew at the time. It seemed prudent for Australia to examine the technology as insurance towards possible future needs. Secondly, there were some indications that overseas supply of research reactor fuel could become uncertain, and possession of enrichment know-how could be important if we had to make our own, even at higher cost. The needs in terms of quantity would be relatively small, and we were already having difficulties obtaining even small quantities of enriched uranium for irradiation testing of experimental fuels. But the predominant reason was the nationalistic desire that if economically viable, we should process our minerals at home, rather than being a quarry for Big Brother. However, because of the sensitivity of the subject, the Commission decided to keep the enrichment project secret for the time being. It was known initially as Project Whistle, a title for which I claim credit, in parentheses, chosen because of the high-pitched note generated by the high-frequency electrical driving power of a gas centrifuge. Again, we shall go into this topic in detail later. At that time, the Commission became aware that both Atomic Energy of Canada Limited and the United Kingdom Atomic Energy Authority were proposing to study the design of reactor systems using natural uranium fuel, heavy water moderation, and cooled by ordinary water allowed to boil in pressure tubes carrying the fuel. The Canadians had developed heavy water systems to a high degree, using natural uranium metal fuel and heavy water cooling, but could foresee considerable advantages in capital costs and thermal efficiency, and in reducing heavy water losses, all improving system economics, if the reactors could be cooled by ordinary, light water. The UK had its own reasons for looking at such a system. To that time, the UK nuclear power program had utilised mainly the Magnox-type reactors, fueled with natural uranium metal clad in Magnox alloy. Magnesium non-oxidizable, a special magnesium alloy which would not burn in the coolant gas, carbon dioxide. These reactors are enormous and were costly to build. In order to reduce capital costs and improve efficiency, they developed a higher temperature gas-cooled reactor, the Advanced Gas-Cooled Reactor, AGR, using uranium dioxide fuel clad in stainless steel. They had hoped to use beryllium, but results of irradiation testing by the AAEC in HIFAR, see Chapter 4, ruled this out. The AGR did not provide the level of benefit originally expected, and although used in the UK for the second power program, was not considered promising for export, as indeed it proved. Therefore, the UK had nothing suitable as an export reactor, at a time when it appeared that there would be a large and growing market for nuclear power systems. The prospects of using heavy water moderation and light water cooling were attractive, and if achieved, were likely to lead to a commercially attractive system for export. Although the system required some enrichment of the uranium, it was still promising, and a prototype reactor was designed and built. This operated very successfully at Winfrith Heath in Dorset for some years. It was eventually shut down when no orders had been received for the system. Refer Jarvis Bay, Chapter 9. The Canadians called their prototype heavy water reactor system CANDU, Canadian Deuterium Uranium, and the name became the generic description of the system. Therefore, the project to develop a light water-cooled variant became known as CANDO BLW, boiling light water. The British called theirs the Steam Generating Heavy Water Reactor, SGHW, and when the prototype operated successfully, decided to look closely at a natural uranium-fueled version, which they called SGHW-N. The AAEC was very interested in both these projects and sought to be involved. Accordingly, arrangements were made to second staff to both organisations to work in the project teams. In fact, the UK team was very largely made up of Australian attached staff, 22 in all, but of course integrated with the UK AEA design organisation at Risley in Lancashire. The team leader was a member of the Risley staff, Mr Jack Moore, and the senior engineer of the Australian team was Mr Dr. Doug Eberling. One member of the team, Bill Wright, a senior metallurgist, was attached to the UK AEA Fuel Element Laboratories at Springfields, where the SGHW fuel was being developed but kept in close touch with the other members. In Canada, with which Australia had entered into an agreement for cooperation in October 1959, 8 AAEC staff members took part in the CANDO BLW study. The difference in numbers did not reflect any perceived difference in prospects by the AAEC, but rather the fact that the Canadians intended to study CANDO BLW anyhow, for their own program, whereas the UK was influenced in its decision by the expressed interest of the Australians to participate. Thus, the reactor research program at Lucas Heights in 1967 to 1970 had its main emphasis on materials, chemistry, some reactor physics, and the engineering problems of heat removal. But most of the reactor physics, some work on fuels, and all engineering design work proceeded overseas. The Risley work resulted in a completed design study which confirmed preliminary work in Australia indicating the reactor type could be economically competitive. However, the conclusions also supported the UK decision to use low enrichment and not natural uranium. The results of the work on the use of natural uranium fuel in these reactors were not optimistic, for one main technical reason. There is a particular family of characteristics of nuclear reactors which is most important for their safety. It relates to their stability while operating at power. The power coefficient is a measure of the change in reactivity of the system if it tries to increase in power for some reason. It is vitally important that it be negative, so that any spontaneous power increase leads to a reduction in reactivity, tending to decrease the power automatically. In other words, negative feedback is applied to keep the system stable. If the power coefficient were positive, a small perturbation in power level would lead to more reactivity, thence to more power. Positive feedback, a potentially runaway situation. When the reactor is water-cooled, this prospect of a runaway characteristic can arise when the physics of the steam, i.e. the nuclear characteristics of its reactor core, are such that the effect of an increase in steam bubbles in the water coolant is to increase the reactivity, leading to more heat production, hence more steam, and so on. Again, a potentially runaway situation. This is known as the positive void coefficient. The reactor at Chernobyl in the USSR, which exploded in 1987, had such a characteristic. This was known from the beginning of this class of reactor, from the announcement at Geneva by the USSR in 1955 of the first in the world power station near Moscow. But it can be controlled by the reactor control system, provided the reactor core is operated at all times within defined limits. This did not prevail at Chernobyl. It was operator error which triggered the accident by transgressing these limits. But if the void coefficient had been negative, the consequences would have been relatively minor. To my knowledge, no power reactor has ever operated at full power in the non-communist world with a positive void or power coefficient. These explanations are somewhat simplified for the sake of the non-nuclear reader, and some of my physicist friends may scoff. But the safety implications of these positive coefficients are undoubtedly serious and to be avoided. The conclusion of the SGHWN study in the UK showed that it was not possible to use natural uranium fuel in that class of reactor, with boiling light ordinary water in vertical pressure tubes as coolant and heavy water moderator, unless prepared to accept a positive void coefficient. If the necessary steps to avoid this were incorporated in the design, the system would be uneconomic. The results of the Canadian study were similar. The Canadians actually built a prototype reactor, Gentilly, near Montreal, but to my knowledge it was never operated at full power with natural uranium fuel because of the potential for instability. At that time there was a world shortage of heavy water, and the moderator material released because of delays with the CANDU BLW was very useful elsewhere in the Canadian program. One consequence of both of these studies was a strong feeling by those involved that despite the problems with the natural uranium versions of these systems, the basic engineering design, using pressure tubes rather than a large pressure vessel, had much to commend it compared with the PWR and BWR systems. At that stage of development of nuclear power technology, the long-term strength and integrity of large steel pressure vessels was being questioned. The possible embrittlement of the steel by neutron irradiation during the reactor lifetime was seen as a possible problem, and although the pressure tubes would also be subject to neutron damage, the consequences of a pressure tube rupture were relatively minor compared with the catastrophe of a pressure vessel failure. The comparison between these two concepts, pressure vessels versus pressure tubes, arose later when the Commission was assessing tenders for the Jervis Bay Nuclear Power Station. 2 of the 4 shortlisted contenders were for pressure vessel and 2 for pressure tube reactors. Nowadays, there is far more known about these matters, and the spectre of pressure vessel catastrophic failure has largely been laid to rest. It is standard practice to include steel test specimens in reactor pressure vessels and to test some of these samples periodically to study any embrittlement caused by fast neutron irradiation for the whole life of the reactor. Recorder's note. The original text states the Chernobyl disaster occurred in 1987. This is incorrect, but was left unchanged to preserve the authenticity of the work. The disaster occurred in the previous year, 1986. End of Chapter 6. To all my Australian listeners, I have a favour to ask. Australia's energy policy is likely to be a federal election issue in 2019. I created a voter's message to the minister soundbite. If you support nuclear power for Australia, please forward it to your minister to show your support for this industry. More information and a link to the soundbite is in the description. Thank you. Australia's Uranium Opportunities by Keith Alder. Recorded by Logan Smith with the permission of the Alder family. Chapter 7. Overseas Postings and Visits. Keeping in touch. The attachment of staff to AECL Canada and to the UKAE in 1966 was a major exercise, but secondment of individual staff members to work in overseas establishments had been a continuing policy since the beginning. Even as staff returned from the initial major period of attachments to Harwell, others were being sent to a wider range of overseas establishments. These included at different times in the 1960s and 70s the major nuclear laboratories in the USA, the Brookhaven, Argonne and Oak Ridge National Laboratories, and those in Canada at Chalk River. Also, the General Atomics Division of General Dynamics in Southern California. In the UK, people went to Risley, Winfrith Heath, Windscale and Coolcheth, as well as to Harwell. There were also attachments to industries and laboratories in Germany, France and India. In many cases, this was a two-way arrangement. and we had staff attached from time to time from the United States and the United Kingdom. Also, we ran a training school, the Australian School of Nuclear Technology, ASNT, in collaboration with the University of New South Wales, and many trainees from Southeast Asian countries, particularly Pakistan, India, Malaysia and the Philippines, attended the school and then spent periods attached to the research establishment. Fortunately, the Commission also believed firmly that it was necessary for its senior officers to make visits overseas at relatively frequent intervals. This was not always easy to arrange, as overseas travel had to be approved by a panel of public servants in Canberra, not always including technical backgrounds, which sometimes seemed to regard these trips as perks and had difficulty understanding, for example, why a reactor physicist should visit a particular overseas research establishment when a metallurgist had been there only months before. But the AAEC fully supported a regular pattern of overseas visits in 3 general categories: the Power Studies people, a group of engineers studying nuclear power development in the world, by the leaders of the research program, and by individual specialists, particularly when they were presenting original papers at important conferences, or where it was known that a particular piece of work proceeding overseas should be seen and discussed by our own officer working in that field. This policy had considerable benefits both in bringing back to Australia the first-hand reports on what was going on elsewhere, usually well in advance, sometimes years, of publication, and also in promulgating what we were doing in Australia. It was very valuable for our people to be seen and known in the principal places of importance in nuclear development. There was, from the beginning, a strong element of Old Boys Club, and membership led to access and discussions not otherwise available. I benefited greatly from this policy, in that I managed to go overseas on technical visits almost every year, and sometimes several times if the circumstances warranted. In my job, I had no contemporaries in Australia, but there were lots of other directors of nuclear research establishments overseas, and I got to know most of them and found we had lots in common. For example, in our early years we had a close relationship with the Oak Ridge National Laboratory in Tennessee, with staff secondments both ways, and I enjoyed particularly my friendship with Dr. Alvin Weinberg, director, John Swarthout, his deputy, and Bill Manley, then director of their gas-cooled reactor program. All came to visit us at Lucas Heights. Similarly, many of us had good friendships with the leaders of the atomic energy programs in the UK, Canada, France, and Japan. Most of them visited us at Lucas Heights at some stage. Probably my most memorable trip was my first to Japan in September 1961, when I had the honour of being given Dr. Ryokuchi Sagani as my guide for visits to the laboratories at Tokai Mura, about 160 kilometres north of Tokyo. Dr. Sagani was by then the Emeritus Professor of Physics at the University of Tokyo. He had studied with Lord Rutherford at Cambridge before the war, and it was to him that the Americans had addressed a letter after the Hiroshima bombing, explaining what they had, but he never received the letter. These trips overseas were hard work, involving lots of short stopovers and onto another establishment the next day. When one visits a big laboratory and sees, say, 10 specialists in sequence, each one is fresh and ready to talk about his work at length, and after half a dozen or so such dissertations, the humble visitor is beginning to wilt. But the benefits of knowing the people and what was going on, I believe, far outweighed the cost of these trips. Far from being perks, on numerous occasions I had to curtail the itinerary proposed by an enthusiastic scientist, who would try to fit in so many visits and discussions that he would wear himself out, with little or no opportunity for rest. One particular trip I made, in company with Brian Hickman, when we were both still located at Harwell, was an excellent example of the cooperation we received as a result of bilateral agreements. In June and July of 1957, we spent 9 weeks in the USA and Canada studying the design, construction and operation of hot cells, high activity handling laboratories using heavy shielding and remote controlled manipulators, which we knew would be essential to handle the fuel and experiments from the new high flux Australian reactor, HIFAR, then under construction at Lucas Heights. At that time, there were no such facilities in England or in European countries. The US government laboratories and US industries gave us open house to inspect their laboratories, and so did the Canadians. The information we obtained was invaluable when we came to design and construct the hot cells at Lucas Heights in time for full power operation of HIFAR in 1960. End of Chapter 7. Thank you for listening. The next release, Chapters 8 and 9, cover the International Conference for the Peaceful Uses of Atomic Energy, an international forum for the sharing of nuclear technology, made possible after the Atoms for Peace initiative by President Eisenhower. Chapter 9 talks in detail of the rise and fall of the ill-fated Jervis Bay nuclear power station proposal.